Okay. Okay. So, I'll share my screen. So I'll put Jamboards in the step-by-step for week 3 today, Monday. And the Zoom link is there. Well, you're already all here in the Zoom, so it doesn't matter. But and I have an outline for today. So what I was thinking of is I'll treat today like a lecture, but the material I go over, I'll try to like go over it in depth so you like kind of master it today. And then those who can't attend today's lecture, I'll have the video, but I'll also go over the material kind of like quickly on Wednesday again, assuming we can get back together. Because I know some people can't attend this because they don't have like their internet's out or something. Maybe their power's out. So I don't want them to feel like they're lost, but they'll have opportunity to watch the video of this. And also I'll cover that material kind of quickly on Wednesday. So let's go over the lecture outline. Oh, and then I totally completed my lecture outline. I had so many things going on lately. So let's see what we got now. So, okay, we got if a strong base, bad leaving group, bad. Sounds like the dog's in trouble. And if it's a weak base, if something comes off as a weak base, that's a good leaving group, good, like happy sky there. So today I'll start going over some chapter 9, more alcohol and ethers. Chapter 8 with alcohol. Now we're getting more alcohol and ethers. Pro tip, check through these office hours. I'll have office hours today too. I'll just continue this Zoom session through office hours. And if you want to help some people out, you can donate blood. We have a blood drive and you can get extra credit. Let's see, when is the blood drive? So there's a blood drive tomorrow, should be, assuming we'll be back open. And Wednesday, there's links here. You can make an appointment. And if you go do that and let me know, I'll give you extra credit. And we'll have blood drives throughout the year. If you do multiple of them, I'll give you up to 3 points extra credit. So if you do like 3 blood drives, don't give away too much blood. 3 is plenty for a semester. And then there's another cool opportunity for us. There's this scientific literacy, art, and community in the face of a shifting environment. There's this thing that's going on at Sierra College. The applications for it are this month, the 13th, February 13th. And here's some details about it. It looks kind of cool. From 10 to 5 p.m., you'll help out with this event and you'll get paid $100 and food and drinks. And I'll give you an extra credit point. And these kind of things are good to do because you can just save them for your CV or resume. So you can say like, oh, I was an important member of Sierra College community. I helped this and that. I keep track of this too, because I give you the extra credit points. And then if you ask for a letter of rec, I include that in the letter of rec. Like, ooh, so-and-so was an important member of the Sierra College community. They helped with the scientific literacy thing, the Dino Day, they donated blood. Makes you look good. And then, oh, those of you who've switched or are going to switch to the new Monday, Wednesday section, online, it's going to say we start at 7 a.m., but you don't have to show up till 7:30. Because online, it thinks it's a 14-week semester, which means you had not attended any labs so far. Like the first 2 weeks, it assumes this 14-week semester, it assumes you never had a lab. So they want us to have longer lab times to make up for that lost time. But we were actually in lab for those. So I understand that we can do a 7:30 to 10:35 lab, the normal amount of time. So you don't have to show up at 7. And then, but when you do that, when we take you out of the normal lab section you're in, all that information about you is lost, all your grades and all your high-risk waiver and stuff. But I've already downloaded your grades and then I hand input them back in the new section. It's a pain, but it's going to work out better than nothing. But that means you have to do that high-risk waiver one more time. So sorry about that. And thanks for switching, those of you who did. Oh, the ad code doesn't apply anymore because we're past the ad drop deadline. So the way people are getting added to this new section is they are I just give their information to Science Math Division office, and they have to do the dropping of the one section and adding of the new so that it drops and it is erased from your record, that drop. It's not like you dropped in a W or anything like that. So that's why. So you just have to let me know you want to switch at this point. I was confused last week. I didn't realize the ad drop deadline was on the 4th on Sunday yesterday. So I thought I could just give you an ad code for the one you have to drop. Whatever. Okay, exam one next Wednesday. Not this Wednesday, but the following Wednesday on Valentine's Day. And I'll give you more details about that. And here's just the regular links I always have on here for you. And work through your notes today as if they expire. Boom, boom. Don't get them sour and chunky. So if you look at them today, it looks like that. You wait and they start to get gross. All right, so before I do this retrosynthesis helper, let me do a couple of things. I got a couple questions. So I had a question, will the new lab section start Wednesday? And I'm saying, yes, it will. So it should. So this Wednesday, assuming this campus isn't closed, I'll meet all of you at 7:30. The new students who switched into that new lab, I'll meet them at 7:30 a.m. on Wednesday. And I'll basically be at school 7:30 a.m. Monday through Thursday, because I have now Monday lab 7:30s. Monday, Wednesday lab starts at 7:30, and I have a Tuesday, Thursday lab that starts at 7:30, as I've always had. And then on Fridays, that it's considered the lecture for the new section, but I'm not going to treat it as a lecture. I want everyone who's in the early Monday, Wednesday lab to just come to your normal lecture this time, Monday, Wednesday. And then on the Fridays, I'll be on campus from 7 to 10:50, and I'm just going to open that up to everybody. You can come in as like an office hour or do stuff in lab. But it's actually going to be more time for you, which I think that a lot of you will like, is if you're free on those Fridays. Okay, any other questions about that? And is there anybody else who wants to let me know that they want to add in to the new lab section? Here, let me check something really quick. Is this one? No. I'll get to some work soon. Sorry. Here, actually, I'll tell you what I'll do. While I'm doing this, I'm going to make up a problem for us to work on. So let me go to our first Jamboard. I imagine we'll probably use more than one for this. So let's do this. Yes. Chapter 9. Let's start with this outcome 4 real quick. Okay, so I'm going to write up some sample problems for this, and I want you to try working on them. So here we go. I've got an alcohol here, isopropyl alcohol, or 2-propyl alcohol. And then we're going to make it into an alk oxide. So this is the alcohol. And if you have questions and you're comfortable, just feel free to unmute and talk to me. Alk oxide. So we're going to make this into an alk oxide. And one way we can do it is with the LDA, lithium diisopropylamide. So here's LDA. Very strong base, sterically hindered. It's got the negatively charged nitrogen and lithium. That's where the L comes from. Lithium diisopropylamide. So this is LDA. And this will create our alkoxide, our deprotonated alcohol. Just acid-base chemistry. And diisopropylamide. Okay. So what I'd like you to do is add the curved um, curved arrows and calculate K equilibrium. And what I'll do is I'll take and I'll copy this, screen capture this question. Some more panels. And I will go into, wait, I'm already there, huh? The sharing of this, and I will make it editor. I'll make all of you editors. Duplicate. Yeah, there we go. So can you, I think since we got kind of a lot of people in this one, let's go a few people per panel. So can you go to a panel, like panel 3 or 4 or something, and then write your name on it? And once there's about 3 of you on a panel, let's see, 3 times 10 would be 30. Yeah, 3 would be good. Once there's 3 of your names on a panel, one of you could take turns writing out, working out the problem and helping each other work out the problem. Okay, probably got enough panels. We'll see. If we need more panels, feel free to add more. So I see like on panel 2, we got Emma, and then others, a couple more people join her. Write your name there. And then Fred's on 3, looking good. Nobody's on 4 yet, or 5. Liv's on 6. Zoe's on 10. Sid's on 12. You can see who's your favorite. Like, oh, should I go to Zaps or Zoe's or Sid's? All good choices. So Anthony, you asked me, may I have access? I'm not sure access. Let me see. Are you on 12? Oh, maybe it was before I opened it up to everybody, huh? So, okay, cool. And then as you are all working on that, I'm going to start asking some questions too. I'm going to stop my screen share for a minute. So I don't show anybody's private information. Let me see here. Yeah, I guess I'll do it that way. So some of you already told me you can't switch or don't want to switch to the new Monday, Wednesday section, but I just want to, and some of you I forgot, like, but so if I ask you this And I've already asked you, sorry, I just don't remember. And I'm not in my office. I don't have those quizzes that have the answer for me. So let me see. Is Sita here? I don't think she is. Let's see her. If I call your name and you're here, but I don't think you are, let me know. I think I don't see Sita. All right, so let me look for another one. Yazan, I forget. Are you switching Yazan? I'm assuming Yazan's here. Maybe he's not here. I don't think Yazan's here. All right, let me check another one here. Dom? Is Dom here? I don't see Dom either. Athena, I already know you're switching. Anthony is already switched. Hannah Corpus. I forget. Did you want to switch, Hannah? Are you here, Hannah? Maybe you're not. Oh, yeah, you are. So, Hannah, would you like to switch into the Monday, Wednesday lab section, the 7 a.m., 7:30 a.m. one? I'm not sure if you're talking to me, Hannah, or maybe you're stepped away or something, but if you hear me, Hannah?
She put it in the chat.
Oh, she did? Okay. How do I get to my chat? Okay. Thanks, Hannah. Not switching. Okay, cool. And then okay, and then let's see, is Michael here? I don't see Michael. All right, Zoe told me she's switching. Wesley, I forget. Did I already switch Wesley over? I think Wesley's already in, yeah. Mikhail, are you here? Maybe not. Tristan's already switched. Grace, are you here?
Grace and Mikael can't switch because they both have like a class before.
Okay, thank you. Angie, I thought Angie was saying Angela. No, Angela, was you saying you could switch? Maybe you're not here though. I don't see Angela. And then Liv's already switched. Zap, were you gonna switch? I forget.
No.
Not switching. Okay. Thank you. And Lily is, Tanner is not. Sid is already switched. Aaliyah is not here, is she? Can we switch? Nikita, did you want to switch? I forget. I think you didn't.
Yeah, no.
Not switching. Okay. And then Psalm, I think you said you're not switching too, right? Is Psalm here? Maybe he's not here. And then Chris CW, are you coming? Oh, no, he's not here. Okay, last one. Andrew is maybe not here either. Okay.
Yeah, Chris has a class at 7:30 as well.
Oh, okay, cool. Thank you. Okay, all right, done with that. Let me check on the Jamboard. I'll share my screen again. Um, all right, so Emma and Madison are on panel 2, and I like the curved arrows look good. And on this one, the question for Emma and Madison is about the pKa of lithium diisopropylamide. It turns out that this guy is not the acid, it's the base, right? Whoops, gotta revert my changes. I don't know what happened. So this LDA is the base, not the acid, so you don't consider its pKa. You only consider the reactant side acid, not the base. Caption, that's more good. Red. Yeah. And also the pKa of that, it would have to become a -2 charged thing if it is already -1. So that would be a pKa of like, I don't know, 100. It was too high. It's not going to have it. But the pKa of the amine on the product side, that's correct. And it is 35 minus 16. So that is correct. Looks really good. And then I see Fred over here. Oh, Fred, this guy right here, the pKa of this is 35, not 19. 35 would be for, I mean, 9 would be for the ammonium. Not the amine. So, and then also, Fred, 10 to the minus 17. Would be very reactant favored. It's got to be larger to be product favorites, products over reactants. And then we got Josie, Nikita, and Madeline over here. The curved arrows look good. Perfect. Good job. And then Ariana and Hannah over here. The curved arrows look good. I like the coloring. Perfect. And then nobody's on that one. Josh over here. Your curved arrows look pretty good. Yeah, 35. Perfect, Josh.
I like how perfect is misspelled.
Is it? I keep oh yeah. Perfect. Actually, I should just leave it that way. Rahaf. You're just missing a little bit of it's probably because you're trying to write on a mouse or something, but you're just missing a arrowhead there, Rahaf, on that one. Otherwise.
Yeah, I'm using hotspot because we don't have electricity.
Oh no, shoot. Is it yeah, I bet is it PG&E is closing, turning off electricity to prevent forest fires, or is it like poles went
Our
down?
power line just completely fell off. Like my whole
Oh,
neighborhood doesn't have it.
damn.
Yeah, I haven't had power since yesterday at noon.
Oh, wow.
Yeah, same thing.
I'm
Oh,
at Whole
Jenny.
Foods right now.
Huh. So Ariana, you were asking how we explain if it's product or reactant favored. Let me go back to your panel real quick. You are on panel 5 here. Yeah. So the K equilibrium equals the concentration of products at equilibrium over the concentration of reactants. So if your K equilibrium is larger than 1, that means you have more products than reactants at equilibrium.
Thank you.
Yeah, you're welcome. And then and if it's less than 1, then it means you have more reactants. Okay. And Zoe, Sid's got some nice drawings here. I like this. I'm assuming it's Sid. And then, oh, wait, no, Sid is saying that. Maybe that's Zoe. I don't know. Who's the artist? I like the curved arrows. And everything looks good. Perfect. Oh, Sid's all over the place. Tony, too. You're welcome. So, Anthony, looking good. Why did the chicken cross the road? To get to this side. Why did the cow cross the road? Chicken's day off. All right, let's see. Zap. I like the curved arrows. Yep, looks good. Kelly. Curved, everything's good. All right. So let me do this. Actually, I don't need to, I just got an idea. I don't need to save every one of these. I kind of like the handwriting on Zoe's. Let's take Zoe's. I'm going to move you, Zoe, to position 2. And then panel 3, Emma and Madison, I'm just going to erase all your work. What? Because we have the same answer on panel 2. And then I'll write up another question on this one and copy it to the other one. So can you all help me out? On panels like 4, 5, 6, 7, all those, can you erase what's on those? Or just delete, erase, whatever. Boom, boom. There we go. So now I'll go back to this. Bam. Oh, I don't know that. Let's do this. There we go. All right, let's try it with organometallics. That'll be good. So does someone want to tell me, give me an alcohol with like a certain number of carbons?
Do 5.
5, okay. I'll go cyclohexanol. I'll go cyclohexanol. I'll color code this one too. Why not? Make it look good. And then what I'm going to do is I'm going to make an alkoxide with an organometallic. So what do we want to use? It doesn't matter. We can use the Grignard or the organolithium. Maybe we should do organolithium because you've all done the mechanism for Grignard for the pre-lab. So how many carbons do we want for this organolithium?
3.
Okay. This is going to be a good one because this one's a little bit awkward for students, but I'm going to try to make it easier by using my hinge here. And then we'll go boom, pretty much no equilibrium here. And then, so I got my alcohol here. Oh, caption. Alcohol. Okay, so for this one, I want curved arrow. Products, curved arrows, and curved arrows. All right, let me copy this over to our cleaned up panels and do the same thing, write 3 names on a panel. We'll look at this one's already going. Who's on this panel 4? Yeah, I guess you don't need it then. There we go, that's pretty good. Okay, panel 5 has it. Panel 6 has it. Actually, I'll just delete these panels. That'll be faster. So delete 7. Duplicate 6. Duplicate 7. Duplicate. Duplicate. I'm gonna delete 11. Sorry, Hedgehog. You're gonna have to move over to another one. That's an old one. Oh, the Hedgehog keeps getting eliminated. Delete that one. All right, so now we should have, I guess, about enough. I'll make some more just in case, if possible. Whoever's on panel 3, looking good with the curved arrows. I'm guessing that's by the handwriting. Is that Zoe? Panel 3. And then panel 4. Curved arrows look good. And 50 minus 16 is good, yep. All right, good job, panel 4. And then Madison and Josie, and I'm not sure who else, but let's see. The curved arrow looks good. Madeline, maybe? Maisel? It's hard to write on these Jamboards, huh, with the mouse. PKA 16 and 50. Excellent. All right, yeah, we got this. Panel 6 has got it. Nikita on panel 7. Got it. Anthony and Sid. Looks good, except for I'd like to see this bond red. Whoops, I had to revert. There we go, yep. And then Josh. Looks good, but can you add colors over here? And then looking, Kelly, I think you're on the right track. Your H, there it is. Zap. Excellent. Oh, I didn't give you the rabbit. Oh. There you go, Josh. There you go, Kelly. There you go, Zap. All right. Nice. Let's try another one. Okay, so which one's a good one to save? Let's save Emma. I like your work, Emma. Let's do this. I gotta move this bar. Oh yeah, no, I just keep it right here. You're the first one. That's perfect. Okay, you others, sorry, you're getting deleted, so we can make room for more. Delete. Wait, am I doing the right thing? I guess I am, yeah. Sorry, I'm losing all you're probably excited about having like a drawings and stuff. Let's do another one. Okay, 4. All right, now we can use like sodium hydride or potassium hydride. Which one do you want to use? And how many carbons do we want on this alcohol? What do you think, Josie? You're on this panel. Are you able to unmute, or are you in a good spot for that?
Yeah, let's do 3.
3 carbons. Okay, I'll go 1, 2, 3. And then do you want it to be, we'll come up with it again, sodium hydride or potassium hydride?
Sodium hydride.
Okay. So sodium hydride is interesting. It's a sodium cation and a hydrogen anion. Weird, huh? When I was in grad school, I had a friend who was checking his sodium hydride. I think it was sodium hydride. It might have been calcium hydride, but he was doing it dumb. Like the way you can check to see that your sodium hydride is good is you can have a beaker of water and then you drop just a little bit of the sodium hydride in the beaker of water. And if it is good, fresh enough sodium hydride, the hydride deprotonates water to become hydrogen gas, and the exothermic reaction combusts the hydrogen gas. So you get a little pop. But he decided to just turn on the sink and get some water in the sink. and put sodium hydride, and then it started swirling, and then he put too much, and it went down the sink drain, and it made this like mushroom cloud come out of the sink drain. But luckily, it didn't blow up the pipes, because then we were like on this. I think we're on the third floor. It would have leaked all the way down the building, and but actually, even more luckily, that sink always drained really slow. But then after that, it drained really good. So it like kind of cleaned it out, but didn't destroy it. But do not suggest that. And then here we go. So let's go same as before. The curved arrows with colors. And let me duplicate this guy before we write too much on it. Oh, can I ask you a favor? Nikita and Madison and everybody, can we erase you for just a second while I make a copy of this?
I guess.
Yeah. Okay, let me make a bunch of duplicates of it. Duplicate, duplicate, duplicate. Okay, there's a bunch for you all to go find, write your name on, start working on it. Looking good, Josie and the rest. Looking good, Josh. Hannah, looking good. Nikita, good. Oh, I have to tell you something too. I forgot. I have to tell you the pKa of the product side acid. Yep, you got it, Hannah. Nice. Yeah, let's see what we got here. I'll go to the beginning. I think we're on panel 5, right? And 4 was out. Yeah, 4 was out. So now 5. So, or there's a message here. Zoe wants me to select child 2. Okay. And then, let's check this one. Slide 5. Madison. I just like to have some blue here. Madison and Josie. Bloop, bloop, bloop. So I make this one lone pair blue. And then the rest of it, 40 minus 16, 24, looks good. And then I'm at panel 2 here. We've got perfect. Panel 2, Zoe, and then Madison's looking good. Josh looks good. Hannah looks good. Nikita looks good. Sid and Anthony looks good. Bam. Whoever is on panel 10, it looks good as well. Panel 11, no one's on now. Delete it. 12, we've got Ariana. Looks good. That's 11 actually. Then now this other 12, that one's on that one. Let's see. We got a unicorn over here at the one I just made 12. Looks good. Uni. Magical mechanism. This one's a deleter. This one delete 2. Zap. Excellent. Ellie and Lily. Looks good. Oh, I like what Kelly and Lily did. They each used the panel and both did it. That's a better idea than just one of you watching the others. If there's usually, I think for these, there's enough room for that. I like that. Okay, I think I've checked everybody. So I'm gonna delete a bunch of you, sorry. Boom, done. Wait, who am I saving? I gotta save some. I'll save your Zap. So Zap, let me see, where's that? 13, 13 Zap right now. Okay. I'll move that to like, I think it's position 6. Okay, this is 5. Okay, Zap, you erased. Okay, that's fine. We'll keep 5 then. All right, let me bring a little more here. I'm gonna write it up on panel 6, but no, I'll just make a new panel. Actually. I'll write it up on my new panel 6. So nobody write your name just yet on this one until I got it made up and duplicated, please. Oh, this next one? There's no mechanism for this one. That we're not going to do a mechanism for it, but for the next last way to make an alkoxide with alkali metals, last way we're going to discuss We're not going to do a mechanism, it's just an overall reaction. And I'll show you a little video of it. So how many carbons do we want for our alcohol?
7.
What was that?
7.
7. Okay, 7 it is. I'll do benzyl alcohol. Doop, doop, 6, 7. So I don't know about the mechanism for this one, actually. I'm not going to color code it. I'm not sure off the top of my head. But in this one, we're just doing the overall reaction. So you take an alcohol and you add most commonly sodium metal, but it can be the other, what are they called? Alkali earth metals? Sodium, lithium, potassium, cesium. So you just add that metal and it creates the alk oxide. This is maybe the most common way these alkoxides are made. The sodium cation. We started with sodium metal, not sodium plus, and hydrogen gas. So I'm not balanced stoichiometrically, but it's okay. We got the idea. It would be 2 of these alcohols make 2 alkoxides, 1 hydrogen, 2 sodiums. Anyways, so this one we will only learn the overall reaction. And you have to be careful with this one because it generates hydrogen gas, like the sodium hydride. Oh, I skipped up sodium amide, huh? Oh, I didn't even notice I skipped that one. This sodium amide, it's just like LDA. Remember the LDA was the amide, the nitrogen with the negative charge deprotonates the alcohol, the same thing, but it's just a smaller. Instead of having 2 isopropyls, the nitrogen has 2 hydrogens. For this one, we have to be careful with hydrogen gas. So for example, I'll show you what can happen. So normally when you do this, you'd add the sodium very slowly, little bits, and it would bubble hydrogen gas out. But if you add a big chunk, it can explode. So let's look up a video of that. Let's see, sodium. Like, yeah, this is a good one. So let me put that in the jam. Why not? So if you are on the Jamboard, come on over to my Zoom so you can watch the video for a sec here. The sodium metal, it's a shiny metal like other metals, but when it's exposed to air, it gets this gray oxide on the outside of it. And so when you see the sodium, it won't look shiny like a metal, but if you cut into it, and it cuts like butter, it's really easy to cut in the metal, you'll see the shininess inside.
Log it. I'm recording it and.
You're still wants to throw it in.
Oh, Trevor.
I will. Here, give me the glove. All right, I'm gonna just keep throwing it.
Explore. We need a slow motion, man. Hold on. Hold on.
We are
Fella.
recording.
Wait. You want me to throw it real far? Hold on. Wait. Can I throw it real far or no? This is sodium.
That's sodium. Yeah.
This is
That's
really,
fine.
very carefully monitored experiment here. Sorry about the Blair Witch Project here on the filming. There it is. It's generating hydrogen gas, which will combust.
And it explodes.
Yeah. And then the chunks of it were blown in the air, and when they land outside of it, they'll explode as well. So in lab, you're not using a big fistful of it. You're using a little like
That's sodium.
teaspoon. See, there's like a piece that fell and then exploded off to the side. Surprised this video is still up. This is definitely not safe. You'd think they'd be like, oh no, let's not let everybody know how to do this. But okay. So this is the chat. I don't know if it's a good fishing technique. All right, so should we practice a couple of these without the mechanism? I guess so. Yeah, I'll just say no practice on this one. Okay, so now, boom, yep. Add another panel after this one. Boom. Okay, so let's look at our outcomes some more. Chapter outcomes. I'm gonna go back a bit. Yeah. Okay, so before we do these next two outcomes, let's take a break. Let's take a 5-minute break. I'll be right back in 5 minutes.
Mark, you're still muted, I think. Or at least we can't hear you.
All right, what about now? Can you hear me now?
All good now.
Okay, thanks. Cool. All right, so back to me. I guess I'm there. Am I sharing my screen? I am. Okay, back to the Jamboard. So I've got ethane. And then this is ethanol. Ethanol. And then what would I call this next one? Something we've been making for the break. What's that one called?
Would it be called
Maybe-
ethoxide?
Ethoxy. Or no, ethoxide, yeah. Ethoxide, that's right, yep. And then when we have an ether, let's say we have a long chain, maybe like 6 carbons long, 2, 3, 4, 6. And if I put like the ether off of this carbon, we call this part ethoxy. Ugh. Let me make that red. Ethoxy. So they all kind of make sense, right? Ethane, ethanol, ethoxide, ethoxy. So how do we name this according to IUPAC rules? What do you think? Should I number from the left or the right? Should I have my 1 over here?
Left.
Left, yeah. 2, 3, 4, 5, 6. So the IUPAC name for this is, well, we got to add the stereochem first. So on carbon 2, it's a stereocenter. Is that the R or the S? See someone in the chat.
R.
R it is. Good job. A, B, C. So the oxygen's A, this 3 carbons B, 1 C, that's clockwise. So it's 2 R. I don't know why it's not typing for me. 2 R, 2 ethoxy hexane. Oh, I forgot a dash. Always put a dash between letters and numbers, right? 2R, 2 ethoxy hexane. Does that make sense? So let's make up some practice ones. Let's go. I'll go 5 carbons. Dash it here. Oxygen. We'll just go 1 carbon chain there. And then we'll do. So IU pack name, IUPAC. IU pack name for that one, but for a different one, I'll have you draw. Draw. Okay. I feel like I have to draw it out so I don't mess it up. One here, let's go.
Hello, Mark.
Hello. 1, 2, 3. 3S.
Internet's been spotty today, so
Oh yeah. A lot of people are struggling with power and stuff.
we're having some flooding too. So that
Oh
was
dang, sorry about that.
Eh. What have we been going over?
So there's a Jamboard that's linked in the step by step.
Okay.
Come on to that and you'll see I've kept the work we've done so far.
Okay.
And I'm having people jump on the Jamboards and write their name and try the problems I present. Okay, so I got that question. I'll go ahead and pose that to some jam. New jam. Looks like people are already running with it. Okay, this one I'm gonna delete. This one I can delete. Did I save one of those? Uh-oh. I like panel 2 with Zoe and Sid, I think. Keep the don't erase your panel. It's got everything so far. I'm trying to keep track of it all without losing it. So let's see. 7. I want to keep that one. All right, Hannah, I hope you don't mind. I'm going to delete that panel 9. Panel 10. I'll delete that one too. 11. It's got the old one on there. Huh? Let's delete that one. 9. It's 9. I know they're working on that one already. 10. All right. I'm going to paste these nomenclature questions onto panel 11. I'll paste it twice, so maybe 2 people can be working on it. And panel 12 as well. A couple of you can jump on panel 12 and work on it. And 13. 14 as well. So as far as this, I've already gone past the normal lecture time, but I mean, I'm not even really considering this as like a lecture. I'm considering it as many of you can come, get the practice. And then on Wednesday's lecture, hopefully we're back in person. I'm gonna go over this same material quickly though, and then go on to the new stuff. But I'm going real slow right now because I figure, hey, we got the day, let's use it. So if you have to go to another class or you have some things coming up, don't feel like, oh, you're flaking. No, you're fine. This is all extra. If you have to leave, that's totally fine, but I'll be here till I could just keep going until 2, like I normally would with office hours. And I can answer things besides this recent stuff. If you have questions about homeworks and things. All right, so Zoe. Two S2. Oh, this one's it's this one's oops. Whatever changes. Josie, you asked about homework 15. I could definitely do that. Let me just finish up this last
Oh, yeah. I just at some point. Thank you.
Cool. Yeah, you're welcome. And then on this one, I'm on panel 2. I think this is Zoe. So Zoe on this guy or Liv? Oh, is it Liv? I'm not sure. But on this one, it's methoxy, not ethoxy in this case, because it's just a methyl. So it would be 2s2 methoxy pentane. Yeah, there you go. And then for this one here, for the one that I asked you to draw from the name, I got 8, you got 8 carbons, that's good. You got the methyl on 2, it's not a stereocenter, so that's good. And then you have the right thing, that is propoxy. Good job. It's propanol, 3 carbons. But now the stereochem I said was S, right? So no wiggle. Wiggle would be R and S, huh? So what I like to do on these when I'm not sure, I just put the wedge to start because that's easier to determine. That means the hydrogen's back. And then if it's correct with the wedge, if it is S with the wedge, then I just keep the answer. But when I check it now, it looks like it's wrong. Huh? That's R with the wedge. So then I just change it to dash. Yep. And then on panel 3, Emma, A, B, C, R, 2R2 methoxy pentane. Very good. And then for this one, I think, yeah, you have to dash that. Very good. That looks perfect. Let me see. I gotta get a image. Yes. So Madison and Josie, your structure looks good. And another one, I forget what was the question. Yeah, that's R. Is it R, S, A, B, C? I'm confused now. Here's my original question. Which panel did I write this on? I think it was here, huh? Yeah, so this guy. Oh yeah. So I think it's Liv on this first panel. So Liv, I think this is R. With so B, C. Yeah, that's R. We need a wedge on that methoxy Liv or Zoe, I'm not sure. Okay, and then that looks good. Two R, two methoxy pentane looking good. Zap. Boom, that structure's good too. So Madison, I think this is R. Two R, two methoxy. Is it A, B, C. Yep, that's R. But then the other one's good. Yeah, Fred, you got it right. Good job, Fred. Both of them. And then looks good, Tanner. Oh yeah, you did yours a little different, Tanner. I think you got your numbers off on this one, Tanner. So we got to go 1, 2, 3. We need the propoxy on 3 and the methyl on 2. But the first one was right.
That would totally switch the well, that would just switch the groups, right? That
So,
should
so right now you have the propoxy on 4. So you just kind of you got to push everybody over 1.
yeah, but then it'll be
An ant. All right. 2R2 oxy pentane.
that right.
Yeah, looking good. Is that you, Tanner? I was looking at another one, but I come back and look at yours. What? Oh, you moved it on me. No, I'm moving it here. uh, was someone and said something? Was it you, Tanner? Do you need help?
Yeah.
So first, erase your meth. Wait, this.
I'm on 11.
Yeah, erase your methyl and your propoxy. And then number your 8 carbons. And then Lily, the first one. Are you still here, Lily? Oh, I'm feeling Lily. I might have to step away. Yeah. Okay, and then Josh. So Josh, that first one is not S, it's R. But the drawing you did was right. The drawing you did was correct. Mhm. Okay, nobody's on 15. Okay, good. All right, so I got a question about homework number 15 on homework J from Josie. I hope she's able to hang out.
Yeah.
Okay, cool. So I'm gonna go over, I'll tell you what, I'll go to panel 15 for number 15. Let me pull it up.
I think I fixed mine whenever you have a chance.
Okay. This is a good one. So Josie, I posted number 15 on panel 15 here. Can you tell me what you got so far? I'm gonna real quick look at Tanner's. He's got it. Now you got it, Tanner. Make sense? So Josie, what do you got so far for this one?
So my initial thought process when I was looking at the unknown A, the data that you gave us, I saw the two tall lines and I was like, oh, bromine.
Got it. Good.
Yeah, subtract 108 or 79 from 108 and then do the rule of 13.
Nice.
And so then for that, and based off the HNMR peaks, since it's just a quartet and a triplet, that it would just be it would be a bromine attached to an ethyl.
That
So
seems right. Yeah. You already got A?
yeah, yeah.
Good, good. Okay.
And
Nice.
then yeah, and then for B, the lithium would just replace the bromide.
Yeah, that's easy, right?
Yeah, and then it was C and kind of D of like then looking at the mass spec that you gave us because I know, like I feel like I know in D or at least like in 1A there needs to be like a ketone so then an alcohol can form in D, but then I was getting like a little stuck.
Okay, so unknown D, IR shows an alcohol, right?
Yeah.
And so did you do the rule of 13 on that one?
Yeah, so I initially got C6H8, and then when I added the oxygen, it was C5H4O.
I got C6H16
Oh,
Second,
because
C5.
the remainder's 10,
yeah, wait, that's me.
but I still wasn't able to come up with the correct thing.
What was the formula again?
It would C10 or C6H16.
Initially, before you add the oxygen.
Before
So
C-
6 times 12 is 66, 72, and 16. Yeah, that'd be 88.
yeah, and then once you
Also
add the
minus-
oxygen,
Yeah, minus CH4 plus O, right?
yeah, so then C5H12O.
Yep. C5H. Oh, cool. Let me see,
Okay.
that 88. 5 times 12 is 60 plus 12, 72 plus 16, 88. That's looking good. And it has 4 carbon signals, right? I don't give you the spectra, but I list off 4 there, right?
Yeah.
And 5 carbons, 4 signals. That makes sense. It just means it needs some symmetry, right?
Yeah. So wait, 1, 2, 3, 4, 5, 3, 6, 7, 8, 9, 10. Okay, so I think I got that structure too, where it's it has 2 ethyls on the end, followed by a 2 carbon chain and then an oxygen. Or
Can you draw it on the panel. Draw on this
oh
panel.
yeah. Sorry.
It's okay.
Ah, sorry, I'm doing this on my computer, so
I know. It's awkward, but it's weird. Even though it's awkward, it's good for learning in a way because it slows you down, even though it's a pain.
I know, so I know I can't really like complain about it. Okay, I can't do dots on this, but I guess I kind of can. So that's initially the structure
Okay,
that
I like what you did. I like what you did there. Yeah. So you got this framework right here. See how I've drawn the blue carbon chain without the alcohol?
Yeah.
And
So
then
okay, yeah.
you put the alcohol on the first carbon, right?
Yes.
And that one won't work for the proton NMR, huh?
Oh.
No, that's where I got stuck.
So but that's okay. And I like the idea that you're like, oh yeah, I need 2 carbons to be equivalent, right?
Mhm.
For symmetry.
Yeah.
So we're almost there. All you have to do really in these situations is just go, okay, I think I got the carbon chain right. Now I'll just keep adding the alcohol at different spots, see if it works. Does this work? And one of the key signals is right here. This looks like, well, here, why don't we do this? Let's pause on that for a second. So how
Okay.
many hydrogens total does this have?
For D.
For D, yeah, how many hydrogens? Got the formula there?
Oh, 12.
12, right? Can you assign those 12 hydrogens to the integrations in the proton NMR?
Yes.
For me, I had a hard time with the C being, is that a singlet?
C. Oh, C is a singlet, yeah.
Okay.
So how does the high hydrogen, like the propyl, right? Those 6 H's, how is that a singlet?
Oh, I'll get to that shortly. I want to first just see if we can divvy up these hydrogens to the integration.
That's a 6, by the way. I'm so sorry.
Yeah, 6, 1, 2. So that'd be 3, 6, 12. That adds up to 12, right?
Mm-hmm.
So you have a 6 hydrogen singlet. So, okay, continue to draw possible. See how this doesn't work? The one I drew, the alcohol I
Yeah.
drew, because this would be a 6 hydrogen doublet, right?
Yeah. So then for it to be a singlet, you can't have any initial.
Draw the same chain and move the alcohol to another place.
Okay. Okay.
I can just tell you the answer, but I think it's nice if you derive it because then
Oh
you
yeah,
go,
no. I need
yeah,
to.
I can
to
use this
do
technique.
Okay. Let me.
Want me to draw the chain up for you?
No, it's okay. It's okay. Thank you though. One, two, three. Okay, I'm drawing it really close, and I know it's not anatomically, but like in that sense. Oh wait, hold on.
You accidentally added a carbon. Here, I'll help you out. Go
Okay.
over to the right here. I got the chain for you. Just add on the alcohol part.
Okay, thank you.
No problem.
Does it matter where the alcohol is?
Yep. So now,
I mean, as far as one of those 3.
Yeah, there's only one right answer. So now, Josie, the one you just add the alcohol to, tell me about its proton signals. Like the alcohol is a one hydrogen singlet. What are the other signals?
Yeah. Okay, so now just just looking at it, I feel like it needs to be that, yeah, that would be a singlet. And then okay, that would be my question if those are still six hydrogens, if the alcohol's in the middle.
They're still equivalent, yeah.
Okay, just want to make sure. So six. It looks like a B. Next one.
So on this one, Josie,
Mhm.
the oxygen is attached to this carbon, which has no hydrogens, right?
Right.
And if it did have a hydrogen, it would show up at 4.
Mm-hmm.
But no,
Oh,
it's 6 hydrogens. They're further from the oxygen. They're more like 1, like alkane region.
okay. Okay. Yeah.
And up above, do you see how I drew the alcohol, the same one you're working with, but I drew it like in with the tetrahedral geometry?
Okay. Yeah.
See more obvious now that though, yeah, those two hydrogens are
Yeah,
equivalent.
those would be okay. Yeah, that makes way more sense. Okay, let me. um,
You're doing good. It takes forever to write these up, huh?
Goodness, like getting a hand cramp. Okay.
All right, and then try to find the A, B, C, D, the integral cuts. I labeled them.
Oh, yep.
Oh, and then did you see signal B washes away? What does that tell us?
Um, signal B washes away. That it's too diluted.
It's a alcohol or an NH bond.
Oh. Okay, hold on. So,
What does it mean by washes away?
I'll show you. So if you take the NMR of this molecule and you report its spectra, it looks just like I've given you, right? Then after you've taken the NMR, you eject the sample from the NMR tube and you add deuterated water, D2O, and you shake it to allow the D2O to exchange with the OH. So what'll happen is the OH becomes the deuterium. And the deuterium on when we're looking at proton NMR doesn't show up.
Does
So
it make a
it's-
weird like D1H1O?
I'm not sure what you're saying. D1H1O?
Well, the deuterium comes from the water, right? And then the hydrogen just goes
Oh, yeah, yeah,
away,
yeah,
or
yeah.
does
Oh,
it
yeah, I know. I'm
attach?
sorry. Yeah, yeah. You will make a, yep. You'll make a GOH, and you will see this now signal. You will see that one in a different spot, you know? But this
that-
one right here, the D will not show up.
Is that like partially heavy water?
Yeah, medium water. It's just it's chunky. It's not too heavy.
Almost expired.
Will not show up in 1H NMR. So basically, yeah, that signal goes away, and maybe and in practice, maybe it only decreases half as much because it only half as much is washed away. But then you're like, okay, that just confirms that's a bond that's able to be exchanged with D2O, and the type of bonds that do that are acidic ones like on O's and N's, but not on carbon.
Mark, just to make sure for alcohols for on HNMRs, those are the ones that like can range from like 0.5 to like 5, right? So it's really you're looking at the signals that you're given.
That's right.
Okay.
A singlet helps with that.
Yeah. So Josie, this molecule matches up well, right?
Yeah, yeah.
Okay, so now if we draw that in to the box D up here. Can you tell me what C is? Because it's got to be something that'll react with that lithium B
Mm-hmm.
to make that. I'm gonna try these headphones that are wired instead of my wireless wasn't working. Tell me if this is working. Can you hear me? Can you hear me?
Yes.
Oh, good, good. Okay, this is better then. Okay, yeah. So what do you think, Josie? Oh, why don't you do this? I'll call this like carbon 1 and 2 from the lithium that
Okay.
came from the bromide, right?
Mm-hmm.
And the characteristic thing of that is an ethyl. So do you see how
Oh,
here in the H1, you see like a quartet triplet? Oh, you're like, oh
right,
yeah, ethyl. And then
right.
also in the final product D, I've got the triplet quartet still. It's
Yeah.
still ethyl.
Okay.
Their parts per million change a little bit, but they're still in ethyl, huh?
Yeah.
So can
Okay.
you tell me which carbons on the final product are 1 and 2, the ethyl?
Yeah. It's loading. Hold on.
That's okay. I know this, you got to be patient with this. It's amazing what it does, actually. We're all able to draw on the same thing. It's incredible, but sometimes it glitches and pauses. You got to just remember how crazy cool it actually is.
First world problems.
And then Zoe's asking about C as well. We're almost there, Zoe. It's basically like a retrosynthesis at this point.
Oh, okay, wait, hold on. I think okay, I'm just gonna do this in red. Here.
There you go. Yep.
Okay, that makes sense. Because then the hydronium is what makes it into an alcohol.
Yeah, it's a you can see the mechanism on it. Adds the carbonyl, O minus.
Yeah. Magic.
It's a
Thank
good one, huh?
you. Yeah, no,
Awesome,
that,
thanks.
that makes sense. I appreciate it.
Yeah, you're welcome. And then one of the things, Josie, the most important thing to get out of this, not just
Mhm.
figuring out this question, but
Right.
was the idea, this is a good concept. You know how we drew up this alcohol, the very first alcohol, and you're like, it doesn't work.
Yeah. Oh, I was gonna ask you about that. Like to explain.
Yeah, so for example, the 6 hydrogens, it would be a doublet because of the one neighbor there, right?
Okay, yeah.
But
Yeah.
since we know it has to be a 6 hydrogen singlet, then we say, well, okay, let me move the alcohol around. When I move the alcohol here, I still get a 6 hydrogen doublet, right?
Yeah.
But once we put the alcohol here, that takes away that one neighbor. So now it's a 6-hydrogen singlet.
Mhm.
And so the concept I'm trying to say is just sometimes when you get to a certain point, draw up a lot of times it's like you only have to draw like 3 things and then you just figure out which one matches, you know?
Yeah. I think also because with like these types of problems, I know obviously we've done it like the past semester, but just like I was like, oh, you can do like the wedge and dashes. And that was like, duh, obviously. But I just didn't think about that initially. So I'm like, I know there's supposed to be it's 6 hydrogens, but I didn't know how to like make that work. So
Yeah,
that was
yeah, you
that was
got
my like thing.
cool. All right. Do we have other questions or want me to make up questions?
You said the homework that would normally be due today can be turned in on Wednesday and it'll be fine, correct?
Exactly.
I guess I could start with one on the Grignard reaction pre-lab. It says, what molecules in air did the intro say Grignard could react with? And I said O2, H2O gas, CO2 gas, argon gas, and nitrogen gas. What should be?
So I don't know. What was this? Did you say argon gas or what did you say that one of them I couldn't quite hear you.
O2, H2O gas, CO2 gas, argon gas, and N2 gas.
I don't know that I don't think it reacts with argon. And I don't think it reacts with nitrogen gas much either, but the others, yes.
Okay, and then might also want to go over the reaction coordinate diagrams on the mother load, which I think is like question 5, and then another question.
Okay. And so I'll pull that up. And then what I'm going to do, Josh, is on panel 16. Zoe was asking about number 16 from the homework. So Zoe, I copied that over there. Let me make sure Zoe's still here. Yes. Okay, Zoe, yeah. So can you show me what you got so far for the rule of 13 on that one, Zoe? You could start writing it on panel 16. On panel 17, Josh, which question from the mother load would you like me to talk about?
So I'm going to turn in that pre-log real quick again, and I'll get it up.
Okay.
It's going to be like a couple of parts on problem 5, and then there's another.
Okay, while you're uploading your thing, Madison was asking about, might be one of the ones you have too, 27 on the mother load. Let me
Sure.
grab that one too. '27, okay.
Yeah, for this one, I'm just not sure really where to start. And a lot of my other questions are just on NMR stuff as well, because I just don't really understand it yet.
Yeah, we'll get you going. More
Okay.
practice will get you better at it. So this is from the mother load. That's 2 words. LIVE, I think. Mass spectrum, 3 below. I'll start on this one for you. I'll help you. You'll help me make it, Madeline. So I'm going to redraw the ketone here. So when it comes into the mass spectrometer, what happens first to it, Madeline? I got that. Do you remember how it gets hit with the electron beam?
Somewhat, yeah.
Here, I'll draw it out for you real quick. We'll get it down. Okay. So as it comes into the mass spectrometer, we have in our mass spectrometer, we call it the filament. Has an electron beam when the filament's on, and it'll hit the molecule and it'll knock an electron off of the molecule. It can knock off an electron from a sigma bond, a pi bond, or a lone pair. What do you think is most common to lose an electron from?
A pi bond?
Actually, usually the lone pair.
Okay.
They're not bonded to other atoms, so they're looser held. So we get this guy, the molecular ion. And this is basically the entire molecule minus one electron. So it has the same mass because electrons are so light. Can you tell me the formula for that molecular ion? Can you type it below it?
Sure.
And then back to this. Now I'm looking at Zoe's rule of 13 she's doing here. Is that 74? Let's see. Yeah, that's 74. Good job. 74 minus 65. I got 5 remainder of 10. Maybe that's the problem, Zoe. Let me see here. C5H14 equals 60 for the carbons. Oh, wait, no. Makes sense. I did my math wrong. 74. That's good. Okay, and then we add an oxygen because of the alcohol. Good. C4H10O. Okay. I think I like this formula. And then 5 minus 10, 0 degrees on saturation. Yeah, this looks good. You got it already, huh, Zoe? That's right. I think I enlarged this too much. Let me just get the problem back on here. So Zoe, that's the reactant, right?
That's the part I was kind of confused about, the whole reactant products thing.
Yeah, so this is the reactant. And then what kind of alcohol is this? Is it a methyl alcohol, primary, secondary, or tertiary?
Primary.
Primary alcohol. So how many hydrogens on the carbon with the alcohol that can be oxidized?
2?
Yeah. And then this is Jones oxidation. So is it going to take them all or just some of them?
Just some?
Or all of them actually, yeah. Sorry. It's either all of them or one of them. PCC takes just one. Do you know about that? Maybe that's what's throwing you off.
Yeah, I think it is.
Yeah. So I'll help you with that. We'll practice that. Because that was probably the week week you missed, basically.
Mm-hmm.
So so you wind up with a carboxylic acid for this one. See how now the carbon that had 2 hydrogens on it right here has 0 now, huh?
Yeah.
That's the full oxidation that Jones oxidation does.
Okay.
Do this for me. Can you come over to our GSAs?
Yeah.
And then chapter 8. Let me know when you find it.
Found it.
And then do you see oxidation reduction? It's on row 108.
Yeah, that's the one I started doing. and
Yeah,
it-
start from the beginning. Click through that one right now, and then
Okay.
just hit me up whenever you have a question.
Okay, thank you.
You're welcome. And I'll come back to. So Madison, were you able to figure out the formula for this ketone here?
Yes. Oh, I'm sorry. I just didn't press enter.
Oh, that's why. Okay, yeah. So let me check. 1, 2, 3, 4, 5, 6, 7. C7H14. Oh, perfect. Okay. So now how much does that weigh if we use for mass spec like this, we use the most abundant isotopes to get the molecular ion. So carbon, you'll just use the number 12, not like 12.01.
Is it 114?
Let me do it real quick. So it's 7 times 12 is 84 plus 14 hydrogens plus 16. Did you get 114, did you say?
Yes.
Yes. Okay, so can you find that on the mass spec? On
Yep.
this guy, which one is it?
It's gonna be the little one.
Do you know how to use the here, I just screen captured the molecular ion. Can you drag it over to the peak
Sure.
or draw an arrow to it? Do you know how to use the drawing tool on these Jamboards? That little pen at the top of the.
Yeah. I'm doing it on my computer too, so it's a little
Yeah, it's awkward. You'll get the hang of it though.
that one.
Perfect. Yes, yeah, that's the one. And then what's the one right here? Do you know what causes that little guy?
No, I don't.
I'll help you. So what it is remember how I said you have to add the mass with only the most abundant isotopes?
Mm-hmm.
Well, sometimes the molecule will have other non-abundant isotopes. And that's what we call an isotope peak. So if we take this same guy and I say one of these carbons just happens to be a carbon 13, maybe this one, it would weigh exactly one more, right? Because it's usually we're talking carbon 12. That's the most
Mhm.
abundant isotope. So if we get, when we have a molecule that's just like one carbon 13, it could be any of the carbons, then it would weigh one more and it would show up right there. Does that make sense?
Yep.
Yeah, so this one above is 114 mass to charge, the molecular ion with all the most abundant isotopes. And this guy is 115. Because it's got a carbon 13. Carbon 13 could be one of the other carbons, or it could even be that they're all carbon 12s, but one of the hydrogens is deuterium, but that's less likely. So here's a quick thing about isotopes. So like the carbon 12 is about like 98% abundant, where carbon 13 is about 1% abundant. So the smallness of that, does the smallness of that signal make sense for that 98 and 1?
Yeah.
Yeah, good. Abundant. All right. Okay, now let's do some cleavages. So this molecular ion, it's very unstable. The oxygen is not happy. It has no octet. It only has 7 electrons around it and a positive charge. So it most likely will just fall apart on its own. It breaks apart before it can reach the detector. And when it does that, then its fragment shows up on the detector, not that. So I'll show you some of these fragmentations. So what do we call this carbon right here? Do you remember what we call this? Like our Grignard's attack it, so I refer to it as something.
The electrophile?
It's an weak electrophile, yeah, but it's also a carbonyl carbon. Does that make sense?
Mm-hmm.
All right, that's the carbonyl carbon. And then one step away from it, we refer to these carbons as alpha carbons. That's an alpha carbon, that's an alpha carbon. And then if you go another step from the carbonyl, it's beta carbons. Makes sense, right?
Mm-hmm.
Okay, so the first thing we're going to do is an alpha cleavage. We're going to cleave off one of these alpha carbons. So I'm going to do the right one first. This single radical electron is going to come and it's going to make a pi bond with one of the two electrons between the carbonyl carbon and the alpha carbon. So it comes out and it goes dink like that and makes a pi bond to the oxygen. And then this other carbon, the other electron, I'm sorry, goes to the alpha carbon. See if you can draw the product of those curved arrows. That's half. Have you seen the half arrows before?
Yes.
Okay. See if you can draw the product for that. All right, Josh, I haven't forgotten about you. Oh, you put some problems up. Panel 18, I like it. So
I got more, but I can start with these.
it's like reactants. Number 5 looks good. Was there a particular question or you just wanted me to double check it?
Everything's right. So the curve mechanism, the direction coordinate diagram, in the transition states.
Yep, they all look good. Both problems.
Guess I'll get the next ones then.
Yeah, let's see how you're doing. So Madison, not quite like that. So what's going to happen is this. I'll give you the first part, Madison. It's going to here, actually. Is it okay if I erase what you got so far?
Yeah.
So it's going to, the two electrons that are holding this alpha carbon to the carbonyl carbon, they're breaking apart from each other. So that bond's going to be broken. So what you're going to end up with is a triple bond to the oxygen. And then carbon, the alpha carbon, it's going to have just a radical on it. And then there'll be still a lone pair on the oxygen. I drew it linear because now that carbon with the oxygen's a triple bond. And a plus charge still there. Is that making sense?
Yes.
All right, and then what happens, Madison, is when these charged particles travel through the mass spectrometer, a strong magnetic field bends their path towards the detector because they have a positive charge.
Okay.
So this radical right here, will it be detected?
No.
No, it doesn't have a charge. Its path won't be bent. But will this one be the oxygen with the plus charge will be detected, huh?
Yes.
Okay, can you calculate how much that weighs with the most abundant isotopes?
Sure.
So I'm looking now at panel 19 for Josh. So Josh, I found one little correction. So this guy should be like -1/4, not 3/4. Because it starts off as 0. And then the cyanide starts off as -1. You might have forgotten that in the thing there. And so it should be -3/4 because it's looking like it's close. It's like reactants, it's close to -1. Do you agree?
Yeah. That's what I wanted to ask about. mainly the transition states when going over these. 'Cause I'm not or transition states and the fractional charges, but mainly that when going over these. 'Cause I'm not entirely sure of them, but
The first two you showed me were good. This one was just backwards. You got a little confused on that one.
um,
And then, so Madeline? No, Madison? I keep doing
Yes.
that. Madison, did you get a formula for this
Yes.
fragment? What do
Oh,
you
sorry, I
get?
didn't even write it, but it's C3
C3, yeah.
H. Sorry, I'm like on the wrong page now. Sorry, yeah, C3H5O. Sorry.
H50, yeah.
Yeah.
1, 2, 3, H50. That's right. Do you know what that weighs?
It's 57 mass per charge.
Do you see that on the mass spectrum?
Yes, it's the tallest peak.
Nice. Yeah, 55, 56, 57. Yeah, we call that the base peak because everything's percent is based off of that.
Okay.
So what I was asking for in this question is you would like draw it next to it on the spectra like this. Does this make sense?
Mm-hmm.
That's that one. Okay, so now let's I'm gonna shrink this down really quick. Get some more room on the panel. So that was an alpha cleavage to the right. Do you think you can draw the alpha cleavage to the left? And I'll draw this up for you to help you out.
Oh my gosh, 36.
To make it easier, I'm going to put the single electron on the left because I want you to alpha cleavage to the left.
Okay.
See if you can add the curved arrows like I did in the product and then figure out the weight of it and all that.
Yes.
Okay. Yeah. And then do others have questions or you want me to make up some questions?
I'm getting more.
Okay. And then while the rest of you are here, let me give you some practice. Let's do some you know what we should do? Is practice the quiz that's coming up. On Wednesday, we'll have organometallic synthesis and carbonyl addition quiz. Go find it. So here's an easy one. Actually, I'll just open the whole thing. That's good. First parts should be easy. So this is the exact quiz you'll get on Wednesday. And we're kind of running out of room on this guy. Let's make a new one. I'll put 2 on a panel and you can Why won't it respond? It's being weird. Maybe I gotta share it first. I don't know. Oh my goodness. I'm linking a new office hour jam to Huh. Oh, that one's looking weird. I guess I go down the balls. Okay. Okay, so I linked that one, and now can I duplicate this? Duplicate, good. So for those of you who you can continue to listen into the specific questions I have on the first Jamboard, or you can go over to Jamboard 2, working on those problems. Okay, 1, 2. So on this one, I'm back to panel 17 with Madison. So Madison, if I number along the chain here, you following along with me? 1,
Yes.
2, 3, 4, 5, 6, 7. What blue numbered carbon gets the radical?
3.
Actually, it looks like 2 to me.
Oh,
See this
oh
curved,
yeah, sorry, 2.
curved arrow right there? Yeah. So you accidentally added a carbon, huh?
Mm-hmm.
See if you can erase it and fix it.
Okay.
Good. And now can you add the rest of the numbers? Make sure the other side's right.
Sure.
Actually, your numbering got a little off there. You missed the carbon on the numbering. You did better
Oh
off not
yeah,
to
I
number.
did. Okay. Just gonna redo that.
Okay, so it's got the right number of carbons now, huh?
Mhm.
Okay, but there's one other thing missing. Remember whenever you write out reactions, you want to make sure your atoms are balanced. So you're numbering those carbons, it looks like atoms are balanced. And also check for charge balance. So the reactant's overall +1 charge, right?
Mhm.
So the product should add up to an overall +1 charge. There you go. Okay, so which of these is going to be bent by the magnetic field and detected?
It's gonna be the one with the oxygen.
Yeah, so how much does it weigh? And then see if it shows up, if you can find it on the mass spectrum.
Okay.
So I'm not sure if others had to check out or not, but does anybody like want to go on to the new Jamboard and practice those?
I had another one on the last game board.
Okay, I'll get to that, Josh. But Josie, Ariana, maybe yeah, some people have to go, and that's fine too. Josie, Ariana.
I'm also working on the question 27 right now with
Oh,
Madeline.
okay. Yeah, good. Okay, keep going. And then Frederick, others, if you want, Zoe, you could practice those organometallic syntheses on the new Jamboard. What I'm getting at is ask me if you can't find the new Jamboard.
Okay. Is it fine if I just continue to work on homework J? Would that be
It's
okay?
totally fine. Yep, no problem at all.
All right.
85. Yeah, that's the one. Good job. 85 mass to charge. Is it making more sense?
Yeah, it is.
Good, good. So the alpha cleavages aren't too bad, right?
Yeah.
All right, and then the last one is the McLafferty. I'm gonna make this smaller, get us some more room again. Okay, so for the McLafferty, you have to set the molecule up a certain way. You have to set it up in a 6-membered ring. And the 6-membered ring starts with the oxygen, and then it goes to a carbon at 5 and then a hydrogen. I'll explain. So do you see how if I number from the oxygen, it's 1, 2, 3, 4, 5, a carbon, and then a hydrogen.
Mhm.
But this is its like reactive conformation. But I have to make sure I still have the same molecule. Do I still have a total of 7 carbons right now?
No.
No, I need one more carbon right there, right?
Mhm.
Okay, good. And now the mechanism, it's pretty cool. I like it. I'll draw the curved arrows. I want to see if you can figure out what the product is from that.
Okay.
So this is how I see it happening. The oxygen pi bond right here, I'll make it red, swings out on the oxygen. So it's hinging on the oxygen, both electrons, and it's going to deprotonate that number 6 hydrogen. And then hinging on carbon 5, these 2 electrons will make a pi bond between 5 and 4. Hinging on 3, the sigma bond between 3 and 4 become a pi bond between 2 and 3. Kind of a lot going on there. Let's see if you can draw it.
Okay.
Okay, I see your question, Zoe. I'll be right there. But first, let me check out Josh here on panel 20. Yeah, we got a E1 reaction going on. All right, so the first step's exothermic, and you do want to draw that out then. So Josh, we want to see, you only have one intermediate for this, Josh. You have the carbocation here. Like that. And the phosphate.
I think I put all the stuff aside.
But then you don't have a second thing. You don't have any of this. And is it methanol reason? Yeah. So then the methanol comes in and it reacts either at the carbon on the end, the primary carbon, or the secondary carbon in the middle. So you can draw it like so. Like right to there. That's both products come from the same intermediate. So there's only 3 transition states total. So I think you should start this one over, Josh, and draw, like, don't draw the, because, yeah.
Okay.
And then Zoe, I'm gonna go over to panel 5 of the new Jamboards. So you're asking me about last 3 parts of home number 12. That's 3 parts. Well, okay. I think it's this what you mean. So Zoe, were you able to follow me over to this new Jamboard? Cool. Are these the 3 parts as well? Nice. All right, so this first one's just an SN2 reaction. Yep. And this acetate is a good nucleophile and weak base. Since it's a good nucleophile, that means it's good for SN2. And it's a weak base, so it's bad for E2. So when we use that, we'll get major product SN2. So it's going to be just a backside attack. Can you draw the product of this step? Even when those move around on you, huh? What? And then not quite, Zoe. So remember, it's this oxygen that's adding to that carbon. So it needs to be the oxygen here. There you go. Not bad. Zoe, you're the anonymous sheep right now. And we got an anonymous ferret watching over you. Yeah, and then I like to see like lone pairs too, right? Okay, and then the next step after we've done the SN2 is to do saponification. And what that does is it cleaves your ester to give you an alcohol. And so I'd had you go check out the oxidation redox. Were you able to do that yet, Zoe, or were you thinking, oh, I'll check on that later?
I did some of it before,
Uh-huh.
and then I remember I can't say it, sponification.
Saponification, yeah.
I remember that from the lecture a little bit. I caught on. Is that just when the organometallic kind of just makes it leave?
No, I'll grab it real quick. Let me see if I can get a quick, if I can pinch out the mechanism if it's short enough. I think that's readable, huh? So do you see on this what I just pasted onto the Jamboard? Do you see that?
Yeah.
Okay, so I'll kind of talk through it real quick. So you see I've got an ester here, right?
Mm-hmm.
And then we add a lithium hydroxide, THF, water, methanol. And then what it does is it cleaves the bond between the ester carbonyl and the oxygen. So you wind up with an alcohol and the acetate comes off.
Mm-hmm.
And I'm pretty sure I'm going to ask the mechanism for this on exam 1 because we haven't, yeah, this will be on exam 1 and I'll give that in my like exam details. So it's good to know this one. So do you see how the mechanism here is the strong nucleophile hydroxide can add to the carbonyl, which is a weak electrophile.
Mm-hmm.
And then we call this a tetrahedral intermediate because the carbonyl carbon was trigonoplanar, but now it's tetrahedral.
Mm-hmm.
And then the lone pair that was put on the extra lone pair on the oxygen from the carbonyl, it drops back down and it kicks off the OH part, hinging like I made it gold, that oxygen,
Yeah.
wedged out one. So you get your alcohol right there. And then this carboxylic acid is not going to stay a carboxylic acid in a basic reaction. It's going to get deprotonated like we do in lab when we do extractions, you know.
Mm-hmm.
And that's it.
Okay.
So what do you think the product is for this saponification?
It's
Try to draw it.
dry. Yeah.
And then while you're drawing that, I'm going to pause for a second. I'll be back in just a minute. Okay, I'm back. Can you hear me?
Yeah.
Good. All right, so
Um,
we're 1 second, real quick, Josh. So another thing you also get, I like to show this too, even though it's not the main thing for Zoe, is you get the acetate. Okay, before I do that next part for you, Zoe, let me see what, let me check on Josh over here. Yeah, Josh, go ahead.
so the products I write here, is that? I know I have that. Is there anything else I need to put there?
You know what, Josh, there's a lot going on that one. Let's do this. Oh, is panel 20 open? Oh, panel 20 is open. Yeah, let's start fresh over here. So that dude, so I moved over to panel 20. Do you see me over here, Josh?
Okay.
Do you see me over here, Josh?
Yes.
Great. All right, so I got that. So I'll draw a line. I'll say, I forget, it's the tosylate. Yeah. Start with our tosylate. And this OTS, just think of it as like a bromine. It's a good leaving group. We'll talk more about them later. So the first step, the unimolecular rate determining step, will make the carbocation for us. And tosylate. Tosylate's a very weak base, so it's a good leaving group. Okay, so let's draw a line. We'll go. Got our activation energy here. And this is our rate determining step, so this has to be the largest activation energy. And then Josh, does this transition state look more like reactants or products?
I think endo is products, if I remember.
That's right, yep. Closer in energy to the products. So this tosylate's going to be far away. Okay, so my charge then will be for the, it'll be almost full negative here. So I'm going to say -3/4 for the tosylate. And then for the carbocation, it's almost fully carbocation. So it's like +3/4. Okay, that's what you had already, Josh, right? And then methanol can come in. And it could deprotonate the middle secondary carbon or the primary outer carbon, right? Okay, into that. So this methanol and this carbocation, we don't draw them twice. They're only because they both lead to the different products. And so when it attacks the left primary carbon, we get the monosubstituted alkene like that, right? Yeah, thanks. Transition state 1 there. And then if it attacks the methanol deprotonates the middle one, I'll get some different alkenes, right? Disub, are they going to be higher in energy or lower in energy?
Then what?
Right.
Disub
Yeah, right now I've got a mono sub
mono
alkene, right?
higher?
And then do you remember if
I think mono's higher.
higher in energy? That's right. So I got a di sub. I'll have two di subs. They're going to be lower in energy. Do you know which one's the lowest? The di sub cis or the di sub trans? If anybody else knows, they can say as well.
I believe disub cis would be lower in energy.
No, di sub cis is higher. Di sub trans is the lowest. Because these two methyls on the trans can be further apart, less steric hindrance than like these two.
Oh yeah, that makes sense. I was thinking like in my head I had this trans structure, but I called it a cis for some reason.
Oh, that's okay. You know what? If it doesn't work out this semester, you can retake me next fall, 25. I'm totally kidding. I can only make that joke because it's not true, Frederick. All right, here we go. So for the di sub, mono sub, we get an arrow like this, and then I'll do another color. All these activation energies are about the same. We'll talk more about this in chapter 11. And then maybe like finally this, oh, I don't want to make it that big. They're like, ooh, like that. They're all about the same activation energy.
It's disub cis.
And then you can draw like, oh yeah, there's an EA for the red one. EA for the blue one. And an EA for the green one. Call that like 3. I'll call it 2 maybe, huh? 2 sounds good. 3. That's kind of awkward. Blue would be 1. Oh. No, blue should be 2. Green should be 3. Overcomplicating this. And I guess it's 4. Okey-dokey. So let me do the second one first. Transition state 2. So for that one, what does it look more like? Reactants or products?
EXO should be react. EXO's more reactant.
Yeah. So this means that there's a hydrogen still closely attached to the carbon, and the base, oh yeah, good job. The protonated methanol should be there. Is far away. Okay, so the partial charges. Oh, I put a full plus charge. That's wrong. Partial charges here. What should I put for the oxygen? Is it closer to 0 charge in the reactant side, or is it closer to the full +1 on the product side?
Maybe close. The +1.
closer to 0. I'd say like,
Plus 1/4.
yeah, 1/4. Very good. Okay, and then where's the other charge? Is there other charges on this?
By the carbo, where the carbocation would have been.
Yeah, the second carbon,
That
huh?
carbon.
So it's going to be partial positive. Is it going to be closer to 1 or closer to 0?
It's neutral. Closer to. Huh. It's closer to. Well, it gets neutral in the products. Um, hmm. Closer to 1.
Yep. Plus
It's
3/4.
more. Not sure why. It's more.
Why it's closer to 1?
Yeah.
So this guy right here, do you see me circling the carbocation? Sometimes there's a delay. Do you see that laser circling the carbocation?
That and the reactants. You're taking into account for that and not it in the products.
So this carbocation is closer to the transition state than the product, correct?
Okay.
So if you're closer to the transition state looks more like you. So try to draw transition state 3 and 4. And then Zoe, yeah, there you go, Zoe. So you're on the right track here, Zoe. We're just gonna, I'll draw the curved arrows for you. So I can do this. This problem I made up a long time ago. I don't have lone pairs on there. I just draw the potassium right next to the oxygen. Now I'm more specific about this. I like it better, but I haven't fixed this one up. So this is the potassium T-butoxide, right, Zoe?
Mm-hmm.
And then what happens is the strong, sterically hindered strong base can reach out and deprotonate 1 carbon away from the leaving group
Mm-hmm.
when the hydrogen is anti-periplanar and it kicks off the bromide. So you have to adjust this. You won't have that hydrogen anymore, and you're going to have a pi bond, huh?
Yeah.
So add the pi bond there. There you go. And then just add on the rest of the things, the methyls, which you're already doing, you know?
Thank you.
You're welcome. Oh, yeah, checking in notes. I'll be right back. Okay, so Zoe, that one's good. Is that making sense now?
Yeah.
And then the last one, the organolithium is a very strong base. Then a carbon nucleophile if no OH or NH around. So this alcohol that it's in the reactant side, it doesn't have a carbonyl, huh?
No.
So the lithium, the organolithium is just going to act as a base. It's going to make an alkoxide. Remember how we started today off making alkoxides?
Yeah.
And then when it makes the alkoxide, it's going to D3O is going to be added, so the oxygen is going to become deuterated.
Mm-hmm.
Josh, long shot, long. On transition state 3, Josh, I'd like you to draw. I know it's hard to do on here. You kind of did it a little different on that one, Josh. Let me show you what I think. I'm gonna actually shrink yours down, Josh, and so I can have room to write mine out. So I wrote what you drew, Josh, but I screen captured it. Do you see it there? It's not lost.
Okay.
So transition state 3, I'll go ahead. I'll make it green so it stands out a little bit. So I've got, make that guy. The plus charge, I have it over here, don't I? For the, on the, there to the left, right? Do you agree?
Okay.
And so I'm imagining now a hydrogen off of here being deprotonated to the right, and the pi bond being created across here. And I want to have my +3/4 right by that carbon. So on yours, you have the +3/4 kind of like by the hydrogen, if anything, right? And it's because it's probably just hard to draw on here. I get it, but I just, when you do draw it the other ways, I like it that way. See what I'm saying?
Okay.
Okay, and then the fourth one, pretty good. Except for you did, I don't know where you're putting the plus charge. I guess it seems like you're taking the hydrogen off of, it's a little bit different. You're taking the hydrogen, it seems like off this carbon, where I would have taken it off that one. There we go. Good job.
On top. This.
The way you're drawing the hydrogen coming off of this carbon, correct, Josh?
Think so.
Yeah. So then the +3/4 should be off of this carbon. Maybe redraw that one. Let's start fresh on it. And have the hydrogen come off of like this carbon. Because that's what we do for there, you know what I mean? And I'll check it. Be right back.
Um, this one?
Yeah, take the hydrogen off of that one.
Hmm. Oh,
Oh, yeah.
Nice.
Oh. I'll help set it
we
up
get
for
the
you.
dots. Hmm.
Want me to help set it up for you, Josh? I'll get you started. I'm just gonna erase this one real quick. So Josh, see how I draw the beginning of this? I'm gonna go boop, 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 and then it had I drew it on my diagram just like that, right? Do you see how this is the same?
Yeah.
All right. And now which hydrogen will I be deprotonating? One of these two hydrogens, correct?
Okay.
Okay, good. So now that kind of orients myself, so I know I can erase those. That was my reactant. And so I'm gonna making a partial, I'm gonna making a pi bond here, and then one of my hydrogens is gonna come off of here. Can you draw the rest of it? I'm gonna stop the video recording. Let's see, am I still recording? What's this thing? Okay, see. Oh, stop. That's weird. That button goes away.